and if it's positive 90 degrees. So any of you who took your extra class test, a lot of figuring out 135 degrees, there's 75 degrees, and you're going, what's going on? Well, then you get yourself one of your antenna tuners and you get rid of all the reactance in the circuit. So between your transmitter and your antenna, you have a purely resistive load. That's the ultimate goal. To figure out capacitance, or capacitive reactance and inductive reactance, here are the two formulas. And let's see, inductance is in henries, and capacitance is in farads. Two famous people there, Michael Faraday and Mr. Henry, who did a lot of work with inductance. Michael Faraday also did a lot of work with transformers, so I don't know why he didn't get his name stuck out here for inductance, but that happens. Impedance is a mixture of resistance and reactance, both the negative capacitive reactance and the positive inductive reactance. It's a form of resistance for AC circuits. So if you're going to work in RF, you're going to have AC circuits. Biasing a transistor or putting in some matching system, and you're going to use resistors for DC and inductors for blocking AC. But basically, you want to make sure that you're using AC and you need the impedance equation. Impedance is a comprehensive expression of any and all forms of opposition to electron flow, including both resistance and reactance. It is present in all circuits and in all components, even when you don't want it there. Like between the top and bottom layers of a PC board, you have, if they're not connected, you don't have resistance except at multi-megohms. When an alternating current goes through an impedance, a voltage drop is produced somewhere between 0 and 90 degrees out of phase with the current. And it's represented by the letter Z.
Phasers.
Phasers are one form.
Yeah.
Resonance is very important for tuning your radio to get the right frequency, for tuning your antenna tuner to get rid of all of the inductive and capacitive reactance to give a pure resistance to your antenna. It's also good for just plain filtering out all those excess harmonics that come through the system. In a superhet, you always have your 4 different frequencies. You have the local oscillator, you have your input frequency, and then you have the local oscillator plus the input frequency and the input frequency minus the local oscillator frequency. So you have 4 frequencies coming out the mixer stage of the superhet. At that point, you need to filter it. So you use resonance to make sure that you're picking just the right frequency. If you're a single sideband person, it gets even more complex because you have to get rid of the carrier and then one of the sidebands. So you only are looking at one sideband, and the filtering is much more complex.
And in the old radios, you used to have a switch, probably still do. Had one set of filters for upper sideband and one set of filters for lower sideband, and you had to switch back and forth to switch sidebands.
Don't they still do that?
Yeah, but they do it electronically now.
I think it's phase.
Yeah.
Resonance occurs when capacitive reactance of the circuit equals the inductive reactance. So in the slide before, it's when you have these two equal, and since they're opposite, all of a sudden you're going to get a 0. It just zeroes out, your impedance becomes totally resistive. And if you have a very low resistance, you're going to get something like this happen. As you come closer and closer to being resonant, you go up slightly, and then all of a sudden at resonance, it just jumps. So that's where only the resistance is in effect, is at the peak of that resonant curve. Resonance occurs, if you take those two capacitive and inductive reactance equations, set them equal to one another, which is what it says resonance is when they're both equal, and you solve for it, you'll come up with the resonant frequency of 1 over 2 pi times the square root of L times C.
It's not very much different, but some people have argued that resonance is when the phase angle is 0.
Okay, that's saying the same thing as this.
Not necessarily.
If the phase angle is 0 here, your capacitive and your inductive reactance should be
Yeah, but the resistance figures into it too.
right. That's why this peak is not infinite.
Yeah.
So this is a form of a model of an antenna system. The AC output of your, or RF output of your transmitter goes into your antenna, and you have some capacitance and some inductance. You always do in any circuit. If you tune that out, then you get to the resonance. So what they did was, I took that equation, I took that circuit, and I figured out the whole thing and went down through the resonance, and we came up with this curve as we swept across the frequencies.
And
At 459 hertz.
that would be considered a high Q at this position.
This is a fairly high Q. A low
Yeah.
Q means the width of the curve is much wider.
More resistance in the circuit for a lower Q.
Well, the difference between, let's see, a good example. You see the coil on the bottom here?
Yeah, if you have capacitive losses and stuff to it,
And
and
that's,
inductive losses.
this is a toroidal coil, and it keeps all of the magnetic field inside of that circle. Well, it has a broader Q than does a solenoidal inductor, one that's, so if you want to have a really high Q, you don't want to use toroids. But modern systems tend to use toroidal inductors because
You can get smaller ones to do the inductance for you.
right, you use less wire, they're cheaper, faster, quicker.
They wire around a ferrite core or a steel core.
Now we're getting to the new stuff. Radiation patterns is what we're going to be talking about a lot. The radiation pattern of various antennas shows you when you might want to use one antenna over another, how you can modify something in the field, so why you might want to use your vertical, quarter wave vertical upside down. Say you're on a mountaintop and you want to talk to somebody down there. If you did this, you're not going to talk to them. They'll be able to talk to you, but you can't talk to them unless you do this. I'll show you why when we get to the quarter wave vertical. It has to do with its radiation pattern and takeoff angle. Radiation patterns illustrate the way antennas radiate in the horizontal and vertical dimensions. Patterns can be analyzed through antenna modeling software. I'm going to have a few examples of that later if you want to get really bold and model your whole antenna farm to find out how all your antennas interact, or for you, how your dipole interacts with the roof of your building. And for me, I have hemlock trees, and when the hemlock trees are wet, 440 goes away. I can't get out unless I really boost the power. Hemlock trees are dry, not a problem. Interaction between various antennas, and well, I just said that. Okay. Here are some example radiation patterns. The one on the right is your quarter wave vertical. So you'll notice if you turn that upside down, all of a sudden your lobes are going to be pointing down. So if you're higher than your compatriot you're trying to converse with, you'll be pointing down at them with your lobe. Their antenna is going to be pointing up at you, and you'll have great contact.
Are we looking down or are we looking?
That's a sideways view.
Don't
want to write the sideways view.
It's a sideways view. This is the antenna like this. And this is of the vertical dimension. So there is some component of this coming out at a very high angle. If you're in the HF band, these can then bounce off the ionosphere, which is a good thing. VHF and UHF don't bounce off the ionosphere, they just keep going. On the right, on the left, your other right, we have two different kinds of Yagi antennas. The big round one, the outer one, is a 2-element Yagi antenna. And on the inside, the smaller one, we have a 3-element. So there's a front-to-back ratio,